Hello, today we are doing 1-3 in pre-calc, which is continuity and behavior and limits. We're going to really focus on continuity today though. Today's date is today. Our objective, going to use limits to determine the continuity of a function and describe the end behavior of the function. Okay, right about now, you guys are probably asking yourselves, gosh, I wonder what a continuous function really means. Well, a continuous function has no breaks, holes, or gaps. You can trace the graph of a continuous function without lifting your pencil. There is a way to do this more mathematically if we start talking about limits going from the left-hand side versus the right-hand side. And that would be more of an honors topic. So we're just going to kind of keep it basic right now and know that a continuous function has no breaks or holes. When I mean a hole, that is just a spot in the graph where it's undefined. All right, there are a couple different types of discontinuities that I'm going to talk about. The first one is the point discontinuity. There's a point outside that graph. That's still a function. It would pass the vertical line test, but there's just a point. The next one is the infinite discontinuity. A lot of times I'll just call that an asymptote. It's still a function. It's going to pass the vertical line test. It's just that you'd have to lift up your pencil. The next one is a jump discontinuity. It's like a piecewise function. You're given usually two functions and given a different domain for each one. So on this one right here, I'm automatically thinking that we're looking at a jump discontinuity because it does have two different pieces to it. And if I wanted to graph it, there's a couple different ways I could go about this. The first one is make that XY table, and for x is greater than -3, it does not include that, so I'm not going to put that in there. That would be part of the other function. But I could have -2, -1, 0. And I would use that part of the graph. For x is less than -3, it is going to include -3. And I would choose numbers that are smaller. I might go ahead and figure out what it is right there at -3 and go all the way up to it because it would include -2.999999999. Then I could put those numbers into the appropriate piece of the function and graph it from there. I went ahead and I graphed it on Desmos, and this is what it would look like. There would actually be a hole for x is greater than -3 right here because it doesn't include it, and right here that would actually be a closed dot. Well, that sure looks like a jump discontinuity. That graph is jumping. Take a second, try this one on your own. Let's see how you do. I would hit pause. When you are ready, hit pause again and check your answer. All right. What I did was I went ahead and factored this. I noticed that was a difference of 2 squares. Your x plus 3's cancel. We know that we're not allowed to have 0 in the denominator, so x cannot equal -3 or +3. one of those canceled out. And that means I'm going to have a hole in the graph at -3 because that's where it canceled. I'm actually going to have an infinite discontinuity at x equals +3. The asymptote isn't written in here, but it's right along there. You can see it. So there's actually two discontinuities here. Actually, let's go back, and I meant to talk about the end behavior of this one. End behavior is what is the graph doing at its extrema. So in this one, as x approaches -infinity, or +infinity, I'm sorry, y is approaching 0. Because as x gets larger, y is approaching 0. Here, as x approaches -infinity, y is approaching 0. We're going to be spending a lot more time talking about end behavior. Just kind of want you to start thinking about it. End behavior, what is the graph doing at the ends? All right, hope you enjoyed this quick lesson.